welcome to the fifth video of Lecture 2. Today we will talk about discrete random variables. In the previous lessons, we introduced the mathematical theory of probability, both conditional and non-conditional. This lesson will talk about random variables, which is an assignment of numbers to the outcomes of a random experiment. And we will also talk about discrete probability distributions, which is just a way of assigning the chances or the probabilities of a random variable having one of its possible values. So this agenda is about introducing random variables and also talking about a very special case of random variables, which is the discrete random variables. We will also talk about continuous random variables, but in a later lesson. So in the random experiment of a soccer match, you may be interested in things such as calculating or estimating the number of goals, the number of shots on goals, or the number of kicks, corner kicks. A random variable is a way of numerically analyzing a random experiment. So a random variable is just a real valued variable that gives us information about the random experiment. In other words, it's a function from the sample space to the set of real numbers. The range of a random variable is the set of real values that the variable can take, that the variable can assume. According to the range of the random variable, we can classify the variable as continuous or discrete. And discrete is when the range is countable, finite or infinitive countably, and it's continuous if the range is uncountable. So let's remember what's a countable set. Well, a countable set is a set of numbers that you can put into a list, for example, or that you can find a correspondence with a set of positive integer numbers. In other words, you can count them 1, 2, 3, 4, 5, 6 until infinitive. Put differently, there's no numbers between two consecutive numbers. Non-obvious examples of countable sets are, for instance, the rational numbers or the even numbers. In the case of rational numbers, you can count the numbers over the diagonals of the numbers that are put into sequence. And in the case of even numbers, you can find a correlation between the positive integer numbers and the even numbers. So you can count them 1, 2, 3, 4, 5, 6 until infinitive. So for instance, the number of members in a Dutch family selected at random is the example of a random variable, a discrete one. In that case, the selection of the family is the random experiment. In this case, the range of the random variable equals the set 1, 2, 3, 4 until infinity. Another example is the number of defective bulbs in a randomly selected box of 20 light bulbs. In that case, the range of the discrete random variable it goes from 0 to 20. We can also consider the random experiment where we perform an inspection on an aircraft. In that case, a random variable of interest may be considered if the aircraft is operational or not. Finally, consider the example in which an aircraft is inspected until the first failure is observed. The number of times the equipment is tested until you observe a failure is considered a random variable. That random variable also finds support in the set of integer numbers 1, 2, 3, 4 until infinity. Let's see another example. Consider the toss of a coin with two trials, so you flip a coin twice. Let the random variable be the number of heads observed. In that case, we have a sample space composed of four possible outcomes. One outcome being heads, heads, tails, tails, heads, tails, tails, heads. And the samples and the range of the discrete random variable is the set with the elements 0, 1, and 2. So a useful function that we can define is the probability mass function. And the probability mass function goes from the range of a random variable to a set of probabilities, so to the range of 0 to 1. And basically it assigns to each possible value that the random variable can take a probability, a chance of happening. The probability mass function gives for each value in the range the probability of happening. So for instance, for 0, the probability that the random variable assumes the value 0 equals 1 over 4 in terms of probability, 1 equals 1 over 2, and 2 equals 1 over 4 again. So this is the formal definition of the probability mass function. Imagine that x is a discrete random variable with a given support with a given range. The function that gives for each k the probability that the random variable equals xk is called the probability mass function. The probability mass function meets certain conditions. So for instance, it's always a value between 0 and 1. The sum of all probabilities equals to 1. So if you explore the range, if you exhaust the range of the random variable, you will add up all the probabilities and you will end up with 1. And if you want to estimate the probability of a given random variable belonging to a given set that is within the range of that random variable, you just have to sum the probabilities. The probability mass function serves to describe the distribution, the chances or the likelihoods of a discrete random variable. But you have another way of doing that, namely using the cumulative distribution function. The cumulative distribution function of a random variable equals the probability that that random variable is equal or less than any x for all x included in the set of real numbers. It's very important to highlight that the cumulative distribution function is defined for all x in the set of real numbers. So it's defined for, the function is defined over the entire real line. And also importantly is the fact that you can go from the probability mass function to the cumulative distribution function and to the cumulative distribution function back to the probability mass function. How? Well, you go from the probability mass function to the cumulative distribution function using the definition of the cumulative distribution function. So at each point in the range of the random variable, you have a jump. Take a look closer at the value of 1 in the range, and at that value you have a probability of 0.5, right? So two things are important to note. First, that there is a closed dot and an open dot expressing the fact that you have a probability of 3 over 4 at the point equals to 1. And also, if you look at the jump size equals to 0.5, which is exactly the probability of the point of the value in the range, the value of 1. So if you want to know the value of the cumulative distribution function at a given point, you just add up all the probabilities of the mass function, all the values of the probability mass function that are behind of the number that you are interested in, including it. If you have the cumulative distribution function and you want to know the probability of a given value, you just calculate the jump at that value. There are some useful formulas that correlate the probability of a random variable over an interval or the probability mass function at a certain value with the cumulative distribution function. And perhaps the most important formula is the one that states that the probability of the random variable being in the set of A and B, excluding A, equals the conditional distribution function at B minus the cumulative distribution function at A. So random variables are just a way to numerically analyze the random space of a random experiment. And that's it for today. I hope that you have enjoyed the lesson, and see you next lesson, see you next video.